Roadsides are unlike other turf systems in that irrigation typically only occurs during establishment. As such, ensuring that best practices are used for this irrigation is paramount. In this session, we will provide an overview of the important considerations for roadside turfgrass irrigation, including a discussion of how water moves in these systems and recent research conducted at the University of Minnesota. In general, roadside irrigation is only required during the establishment process, lasting roughly 30 to 60 days depending on the season, species of turf being grown, and soil characteristics. Proper irrigation practices at establishment will ultimately determine the level of success and long-term quality of a stand. Proper irrigation will also reduce the need for re-establishment, which can be very costly for the contractor. As we work through this module, it's important to understand that various species of turf grasses used in roadside settings might require different irrigation programs. Let's begin by discussing water management background in turf grasses. Irrigation is considered one of the primary cultural practices for turfgrass maintenance, along with mowing and fertilizing. This is because moisture is of vital importance for maintaining healthy grasses. Grass tissue is composed of approximately 80% water, and a constant supply in the soil is necessary to establish turf from seed or sod. Applying too little or too much moisture can ultimately reduce establishment and long-term performance. Too little moisture in a particular situation can result in a lack of seed germination, a complete failure of sodded turf, an increase in canopy temperatures, and a reduction in nutrient uptake. In many roadside establishments, moisture applied infrequently or in insufficient quantities is a larger problem than too much moisture being applied. However, too much moisture can also be a bad thing. Too much moisture applied, either from irrigation or frequent precipitation during the establishment process, can result in poor establishment. When moisture is applied too frequently to seed or sod, poor rooting into underlying soils is often a consequence. Withholding irrigation at the right time will help improve rooting and drought tolerance of new establishments, and this is important as stands mature. Having too much moisture in the soil will also increase the susceptibility to compaction and stress brought on by various diseases, insects, or weeds. In addition, microbial activity, which is important for biological processes in the soil, will be reduced in high moisture environments. Lastly, too much irrigation can lead to soil erosion, particularly in seed plantings. One concept that is important to understand when designing a watering program is how much water might be used by grasses on a given day. Grasses take in water from the soil through their root systems. This water then moves upward in the plant through the xylem and out through the stomatal pores in the leaf surface. This process is called transpiration, and it serves many functions. Possibly the most important functions of transpiration are those of plant cooling and translocation of materials. For example, mineral nutrients like nitrogen. The plant cooling process is very similar to the cooling process that occurs when humans sweat and our skin is cooled by evaporation. The ultimate drawback to transpiration is a loss of water from plant tissue and soil, requiring replenishment through precipitation or supplemental irrigation. The term used to describe water loss from a system is called evapotranspiration, often simply referred to as ET. As the name implies, this process is simply the combination of transpiration of the plant and evaporation of the moisture from the soil and plant surface. Most of the water lost through evapotranspiration is lost by the transpiration process in a turfgrass stand, because the turf canopy hinders soil evaporation. As much as 80 to 85% of soil moisture depletion can be attributed to evapotranspiration. The 5 main factors that affect evapotranspiration are solar radiation, which is generally the most significant, humidity, temperature, wind, and grass species. As would be expected, an increase in temperature, wind speed, or light duration would cause ET rates to increase. Low humidity levels, i.e. low moisture in the air, cause ET to increase. ET estimations can be calculated using these variables, and models are available to calculate this for you. While evapotranspiration might sound like a technical term with little application, it is ultimately the best tool that we have to measure water use on a given day. ET estimations give us a quantifiable reference in deciding how much water to apply over a given period, which in turn addresses the fundamental questions of irrigation volume and application frequency. Generally, when looking at the United States, evapotranspiration rates of grasses will exceed the precipitation rate in the western United States. In more eastern portions of the United States, precipitation amounts exceed the moisture demands of grasses. However, even in the eastern U.S., precipitation is often not synchronized with plant needs in terms of frequency of soil moisture replenishment. This is where irrigation becomes important. ET data can be obtained from various sources. In some cases, smartphone applications are available to estimate ET rates in your location. Monitoring ET is made possible by the use of simple or more sophisticated technology. One simple technology is an ET gauge as displayed on the middle of this slide. Weather stations can also be purchased and installed for more detailed ET modeling. The benefits of utilizing ET models for determining irrigation requirements are that real values can be generated quickly and easily. Drawbacks include the calculations being model-based and not actual measurements of water lost. These systems can be expensive and the outputs they provide can vary by site. When using ET models to schedule irrigation, it's important to understand that different species of turfgrass will have different moisture requirements. KC values are crop coefficient multiplication factors used to determine actual water requirements. Take a moment to review this table of turfgrass species and their KC values. Most cool season turfgrasses can be maintained at 80% ET. For example, if moisture loss on a particular day is 0.2 of an inch, and the crop coefficient for Kentucky bluegrass is 0.8, simply multiply 0.2 by 0.8 to determine the irrigation amount, in this case, 16/100ths of an inch. In the absence of ET models, or for more site-specific monitoring, one of the best tools to assess the soil moisture status is a 3/4 inch soil probe. In this case, moisture status is monitored via the feel method. Soil probes can also be useful in assessing compaction levels of various roadside soils. When turf grasses are moisture stressed, wilting will occur. Wilting is the plant's mechanism of trying to conserve moisture by curling leaf blades, as depicted by the leaf cross-section examples at the top of this slide. Wilting can also be observed when you step on the turf and it does not bounce back. This is often referred to as footprinting. Soil moisture meters are readily available and they can be useful tools for assessing the moisture status of soils in a roadside setting. The particular meter shown in this image has interchangeable probes for assessing moisture levels at various depths in the soil. Drought resistance of turf grasses is a combination of avoidance to drought and tolerance of drought. Drought avoidance of grasses can occur through various mechanisms that can include a deep root system, thick cuticle, small stomata opening, dormancy, and escape. For example, tall fescue is able to avoid drought situations by developing a deep root system in the soil. Kentucky bluegrass can avoid drought by going dormant. Drought tolerance is the ability of a plant to tolerate drought by using less water. Fine fescues are a great example of drought-tolerant grasses. Take a moment to review this table on turf species and their ability to survive drought. As depicted, both tall and fine fescue species have very good drought resistance due to their avoidance and tolerance capabilities. This ends part 1 of this presentation. Continue to part 2 to continue watching.